Welcome to part 2 of lecture 1 of ENGR 2301, Engineering Statics. In this part of the lecture, I'm going to look at Newton's laws and see how those will be applied in the context of engineering statics. So let us consider Newton's laws. Now, you've probably seen these before, at least I hope you've seen these before you got to a course like ENGR 231. This is probably the third or fourth time you've seen these in some sort of course, but let's go ahead and review them and see how they apply, or how we will apply them, to statics. So, Newton's first law, if you want to look at more of a sort of classical way of stating it, you would state that an object in motion stays in motion unless acted upon by an outside force. So if I want to state that mathematically, I could say that V is constant unless a force is applied. And in particular, I should say a net force is applied. In simple systems, we can say force, but really what we're talking about, especially for more complicated systems and static systems and static equilibrium, is we're saying unless a net force is present. So, for example, if you have a block sitting on the ground, for example, just sitting here on a level surface, crudely drawn level surface. If you have a block sitting on the ground, the two forces acting upon it, of course, you will have your block here. You will have a normal force pushing up, holding the block upward, and gravity or weight will be pulling it downward, or pushing, pulling, however you want to think about that. But these two are in equilibrium. The thing is, it's literally just a block sitting on a surface, or it could be a rock sitting on the ground. Anything that's not moving nice and stationary in a ground stationary reference frame. So again, unless a net force. So in this type of system here, we do have forces. We have two forces, but the net force is 0 because these two are going to cancel each other out. So v is the velocity, and when I say velocity, I mean the vector velocity is constant unless a force is applied, or a net force is applied. So this will be more important when you get to, say, engineering dynamics, but for our course here, that's not going to be so important because we're typically dealing with things that are in static equilibrium. So, alright, so what's next? Second, there are many ways to, again, with any of these rules, or I shouldn't say rules, with any of Newton's laws, there are many ways of explaining them or expressing them. But one more classical way of stating Newton's second law would be something like, the acceleration that an object undergoes is, let's say, proportional to the net force applied to it and inversely proportional to its mass. That works, although that is quite a mouthful. In general, though, mathematically, I would express this as the sum of forces is equal to mass times acceleration. And in particular, we could treat this as a vector. The sum of the force vectors is equal to mass times the acceleration vector. So we see, of course, from physics that mass is the constant that mass is the constant of proportionality between acceleration and force. So that's all well and good, but typically in statics class, we're going to go a little bit further and really apply Newton's laws to one particular case of them, one special case. So in statics, then this is very important. In statics, by definition, a static system is one where the acceleration is 0. Now, I could say that it has to be in a co-moving reference frame if I really wanted to, get all physics on us. But at least if you're talking about, if you're in the same reference frame as the object, if you're standing in front of something and you're not factoring into account the rotation of the Earth or something like that, we can treat objects, static systems are those where the acceleration can be treated as 0 in whatever reference frame you're looking at. So a static system is one, or I should probably put a 1 there, where the acceleration is 0. So what does that mean? What does that exclude? Or, so all we know about it is that the acceleration is 0. So, therefore, the acceleration is 0, and that's really all we know. The forces are not equal to 0. Forces are still present. So forces are still certainly present, but the sum of forces is what's equal to 0. So therefore, because the acceleration is 0, we can say that the summation of forces is equal to 0. Again, statics class fundamentally goes and crosses out the A, or sets this equal to 0, and that cancels out the entire side of this equation. And so in turn, since there is nothing to equal or nothing to balance any forces, normally when you're dealing with dynamics problems, for example, you will have some forces on this side and you'll have some accelerations on this side. So these do not have to sum to 0, they have to sum to whatever mass times acceleration is. But in static systems, we say the acceleration is 0. And in turn, that means the forces must sum to 0. So that's going to be pretty important. That will be pretty important, so where the sum of forces will come to 0. And we can also say that it's also important to keep in mind this is going to be a vector sum. So it's not just obviously it's just not a matter of simply saying, okay, well, raw amount of force. Well, if you're dealing with you can't just sum magnitudes of forces in a two-dimensional system or something like that. If you have 3 dimensions, or if you have rotations, we'll be dealing with moments and things like that later in the semester. But for now, we can think of it very simply as the summation of forces being equal to 0. Now, in dynamics class, in our system here, our course system here, we refer to that, our course number for that is ENGR 2302. In dynamics, the sum of forces is not equal to 0, or acceleration is not equal to 0. So therefore, summation of forces is equal to mass times acceleration again. And when you do that, you need an entire semester to explore the implications of that. So this key assumption that acceleration is 0, this is one of the fundamental, most basic assumptions that is behind everything that we're going to work through in this entire course. The sum of forces is equal to 0, or acceleration is equal to 0. Everything we're going to do in this course is going to come from this. There's not going to be really anything moving in this class, again, because this is statics class. And then finally, we are going through all of Newton's laws, the third law. Well, there are many ways of expressing this, but sort of a classical way of saying it is, for every action there is an equal and opposite reaction. Or another way of stating it more precisely, or more concisely, I should say, is all forces come in pairs. All forces come in pairs, and this will be very important, especially when we start dealing with breaking frameworks into smaller pieces. Whenever a force occurs, there is always some other force upon it. So for example, let's say there's a person standing on the Earth's surface. And so they're standing on the surface of the Earth, and just like our block earlier, there's going to be identical, very similar forces acting upon them. What kind of forces are going to act on that person? Well, let me show the Earth over here. Actually, maybe I'll show it down here, just sort of drawing this as a separated free body diagram. So we're going to have weight pulling down and normal force pushing up. But every force must have an equal and opposite partner. So because the normal force is pushing up on the person, therefore that same normal force must be pushing down on the Earth. Same normal force must be pushing down on the Earth. And then in turn, if this were, now I drew this, I'm drawing this as a separated object, or an exploded view free body diagram, but we could, this same would be true whether the person is not literally flying through the air, otherwise the normal force wouldn't be present, but the opposite weight vector will also exist. So basically the normal force is pushing down on the Earth, and the weight force is pulling up. So again, we can see here that forces always occur in equal and opposite pairs. Now this is kind of a trivial example, just a single object sitting on the surface of a planet. But for more complex objects or more things like frameworks, this will be very important later in the semester. So for example, we'll have systems where maybe there is a, let's say there is I don't know, a rod, and then there's a pin joint, and then there is another rod like this. Well, if I were to draw that, and so you don't need to worry about what these are so far. We'll learn about pin joints and rollers and internal forces later in the semester. But if I were to draw this as separated objects, for now, just accept that a joint like this, where one of this member here meets this member here, that joint is capable of transferring both a vertical and a lateral force, or an X and a Y force. So if I were to draw this as separated, two separated points, or two separated objects, and let's call this joint A, for example. This is joint A. I might have, an AX, and in turn an AX, an AY, and a matching, actually, sorry, I'm drawing this on the wrong diagram. Derp. Helps if I get my drawings matched up properly and don't make basic errors. Go ahead and fix that. I want to show these internal forces on the exploded diagram. So let's go ahead and do that. So I'm going to have AX, and we'll see later that the direction that you assume is mostly arbitrary. But if I have AX here, AX will, if AX is pushing the top member to the right, it must be pushing the bottom member to the left, equal and opposite. If AY is moving the top member upward, then AY must be moving the bottom member downward. And again, don't get too lost in this. If this is a little confusing, don't worry about it. All I am doing is using this as an example for how forces occur in equal and opposite pairs. So forces will always be in equal and opposite pairs, and they'll always be in opposite directions. So one, again, forces are in pairs, and two, force pairs will be in equal and opposite directions, or just opposite directions. Force pairs will be in opposite directions. And we'll be using this and the other two of Newton's laws. Well, maybe not one. We rarely use that one in statics. The ones we use most importantly in statics are going to be the second law and the third law. But these are really the foundational principles upon which this entire course is built. So do make sure you're familiar with them. Do make sure you're aware of them. But that will conclude with this portion of the lecture, and we'll be back for part 3.